Hey everyone, welcome to the first video from section 3.3. So in this section we're dealing with the case of complex roots in the characteristic equation for second order linear constant coefficient ODEs. While I'm going through this video, just be aware of some of the interdependency stuff between this video and the stuff for the complex numbers video, which is going to be posted on top of this one, but it was originally meant for section 5.4, just because we're doing things in a different order now because of moving the first exam. So watch those T videos kind of back and forth and figure out how they come together. They work together well still. It still all works, but it might be a little different to follow just because of changing the order of things. All right, so let's get into the case of the complex roots in these equations. So there are two main facts that we're going to use in talking about complex roots for the characteristic equation. So the first is discussed in the complex numbers video and is also covered in the book, is Euler's formula. And that is that if I have the exponential of a complex number, say e to the I mu, so I is just the imaginary unit and mu is some real number, so this is the purely imaginary number, this is equal to the cosine of mu plus I times the sine of mu. And the second fact we're going to use, we discussed the end of section 3.2. And that basically says that if I have a real valued operator, so all my polynomials there are real valued, and I get a complex valued solution, then the real and imaginary parts of that solution are both solutions in their own right. So if y of t equals u of t plus I v of t solves Ly equals 0 with p and q real valued, then L of u is 0 and L of v is 0. Which is the two main facts from previous videos we're going to have to recall here to solve the problems in the case of complex roots. So let's start putting all this together. So we want to solve the ODE a y double prime plus by prime plus cy equals 0. And this has characteristic equation ar squared plus br plus c equals 0. And we're going to assume that this characteristic equation has two complex conjugate roots, which we're going to write as r equals lambda plus or minus I mu. So lambda is the real part of the roots, mu is the imaginary part up to this plus or minus sign. And if you write the formula, you'll see that they have to come in this type of pair because our quadratic formula tells us this, b squared minus 4ac over 2a. So if b squared minus 4ac is less than 0, the only place you get an I is after that plus minus, and it's going to come in a plus part and a minus part, so it's going to come in a conjugate pair. Now, from how we derive this characteristic equation, we know that y of t equals e to the rt solves the problem, solves our problem. But the question comes down to, what is that function? What is e to the rt in the case that r is a complex number? And this is where we're going to use Euler's formula. So if r is lambda plus I mu, let's start writing things out. Y of t is e to the lambda plus I mu of t. Now here I'm taking the plus root. If you take the minus root, you get a similar equation with a minus sign in the middle instead of a plus sign. In the end, we'll see it doesn't matter, so you may as well just take the plus one because it works out just fine either way. So this is the same as e to the lambda t, e to the I mu t. Now this first part is just real, that's totally fine. So I'm going to leave that as e to the lambda t. And now the second part, I'm going to use Euler's formula and write that out in terms of sine and cosine. So it's cosine of mu t plus I sine of mu t. And now to make things extra clear, I'm going to distribute through the e to the lambda t. So my function y of t is e to the lambda t cosine of mu t plus I e to the lambda t sine of mu t. And so this should be our solution. However, say our operator L that we're using for all this stuff models a physical system. Well, what does it mean for a point to be 2I units away from the center? It means nothing. It's a pointless statement. It doesn't make any sense to talk about things being I units away from stuff. So we need to use our second fact where we can split into the real and imaginary parts and get those as both solutions. So what that second statement tells us is that I can actually get two solutions out of this one this thing I just derived. So from this, by taking the real and imaginary parts, we get a solution y1 of t equals e to the lambda t cosine of mu t, and we get a solution y2 of t equals e to the lambda t sine of mu t. And we would like to say this gives us everything, but to make sure we check the Wronskian, and if you check the Wronskian of these two solutions, you get mu e to the 2 lambda t, which again is not 0. If it was 0, that would mean mu is 0, and if mu is 0, my solutions are real anyway, so I don't care. I'm back to the old case as it is. So the Wronskian is non-zero, which means that this guy and this guy form a fundamental set of solutions for the problem when we have complex roots. So once we get all of this, our general solution is what? It's y of t equals c1 e to the lambda t cosine of mu t plus c2 e to the lambda t sine of mu t. And this I will box in again. That's a wonderful box. And now one more point to make before we go to the sample problem for this video, and that's this whole complex valued revalued thing. If you're doing any sort of problem in this class, you should assume that it's supposed to model a physical system, which means your solution needs to be real valued at the end of the day, right? The solution at the bottom, this y of t at the bottom here, does not have any complex numbers in it. It is entirely a real valued solution, and it makes sense to use as, say, the position of a mass on a spring. Those functions entirely make sense in that context, so that's fine. The one above, where there's an I in it, makes no sense in a physical context. And I will say it right now, it's on the video, so it's there. If your solution is supposed to be real valued, and you give me something with a complex number on it, you will get a 0 on that problem. It doesn't matter how much work to get there, you will get a 0 on the problem. You will get no credit for it if you have a complex valued solution where you should have a real one. Now, if you get a complex solution en route to your answer, that's entirely fine. But your final answer needs to be real valued, otherwise you will get no credit for the problem. I've seen enough people mess it up in this class time and time again that I need to make a stress a point about that. If your solution should be real valued and you make it complex, you will get no credit for that problem. All right, so that's it for this video. The next video is going to do a couple examples, but I'll give you one to work on right now, just finding a general solution. So I'll throw it up for you right now. All right, so there's your problem to work on. It's just finding a general solution. Use the stuff we talked about earlier in this video to work that one out. All right, thanks for watching. In the next video, we'll go through some examples of calculating these problems. See you then.